So we did this reciprocal lattice, right? Plane wave is a e raised to the power I k dot x type. This k is like a continuous, and x is also continuous, right? Okay. So but what we are going to do, we are going to choose some specific case. We are going to choose some specific case. So let it be some fixed case, such that the plane wave has a period of a direct lattice space. So the plane wave kind of repeat after you move by a one direct lattice vector, right? So what I'm saying is it has a periodic function in the direct space. You choose some specific case such that you have a periodic function in the direct space, and such case are called the reciprocal lattices, right? Collection of such case is called a reciprocal lattice, right? And which we saw, it's like a Fourier version of that, right? We just saw these two, and this is the construction mechanism, and this is the first Brillouin zone. This we all covered. Okay. Now we did this lattice planes, and in the last class I kind of really convoluted the proof of these planes. Then I thought it can be done more neatly. So when you have lattice, you can make a plane. You can take any 3 points, connect them, and you have a plane, right? And these are called lattice planes. And then you can have equally spaced plane, a family of plane. You have plane and equally spaced version, right? These are called lattice plane and lattice plane families. Just a definition, right? And what we wanted to establish, what is the equation of that lattice plane or lattice plane families, right? So let me start from here. Lattice planes and family. So this is the sum. One thing you should notice, whenever I'm saying lattice, right? One thing you should always know, that the origin is always covered in the lattice, because at the origin you are going to put some point. The origin is not random, so origin is always a point in the lattice. So if I cut a lattice by a set of planes, then the origin will be somewhere in one of the plane, right? That is kind of common sense. And what we wanted to do, we wanted to write the equation of a plane, right? And how I can write the equation of a plane? I can write there is some normal vector n, right, into, let us say I have some r point here, some r naught in some plane, right? I can have this vector, and n cap vector. The thing is, n cap vector into r minus r naught is 0. The dot product between, if I satisfy this condition, I am kind of always okay. So instead of an n vector, okay, so what I can do, I can just open this up. So this is the equation of, let's say, this is 0th plane, this is first plane, and this is second plane. This is like a equation of a second plane, I'm saying. I took one of the plane, you can see the one with the star, right? And I wrote this equation. And then I'm going to generalize this equation to write for any n plane, any of these planes, right? For the family. N dot r, this is n cap r naught, right? What is n cap r naught? It is the perpendicular distance between this plane and this, right? Let us say that this distance is d, then this has to be n cap dot r naught. This is the r naught vector and this is the n, right? So if you are still, and this is like my r naught vector, and this is the plane I am talking, and this is my n cap. So if I take a n cap dot r naught, I will get this perpendicular distance, right? So this is here, the spacing between the plane is d, then this would be here 2d, right? So the equation of this second plane is n cap r vector is equal to 2d.
Sir, but r naught is in plane and n cap is perpendicular to the plane. So n cap dot r naught is 0.
No, r naught is not in the plane. So you see, r naught is a position vector of a point in the plane. This is the plane. You take it from origin, you take any point which you know, right? And then it's not 0, right?
Then sir, equation n cap.
Okay. So what I'm saying is r minus r naught is in the plane. This vector, because so this is like a okay. So you see this r minus r naught vector. If you take these two vectors and if you do a subtraction, how do you do the subtraction? Vector subtraction.
Vector law.
Yes, exactly, right. So this subtraction will give you this vector, right? Then this is in the in-plane vector. So this in-plane vector multiplied with the n cap gives you 0. Guys, it's very good that you ask. I guess many of these might have this doubt. Why? This is like a in-plane vector. It's important to ask these points because these are not there in the books, so that's why I'm kind of putting a little more stress. This is the in-plane vector, right? Now is it fine? This is 2D, right? So this is for the second plane. I just numbered it, this is my first 0th plane, the which contains origin, right? For second plane. If I want to write any equation for a family plane, right, so I can write n cap dot r is equal to m into d, where m belongs to an integer. This is the equation for family of planes. I change m, I go to different plane, right? This is the equation. Let's say, how do you write a equation for a family of parallel lines? I say, okay, y is equal to mx plus c. Instead of c, I will say this is some c belongs to some integer. If you keep changing c, you are going to get a right equally spaced parallel lines, right? So similarly, I am going to kind of this. If I have m as an integer, I am going to get the equally spaced set of planes. So guys, this point is clear. This is very essential to be clear. Okay. Now what I can do, I can just take multiply both the side of this equation by 2 pi. Why I am doing it? Because I just like 2 pi too much. Two pi m into d, and this d is spacing between the plane, right? You see, this is the so this is like I can bring this d in the denominator. This is still same, right? Okay, why I am doing it? It offers me a great advantage now because I can express it in terms of exponents. I like the exponent too much, so I wanted everything to be in the nature of exponents. Or I can even multiply this equation by any integer. It won't change anything, right? Let's multiply this equation by, let's say, p, which belongs to integer, right? So I can say, okay, 2 pi d into p n cap dot r is 2 pi into m into p, right? If I multiply two integer, what I get? Integer. So this m into t also belongs to integer. Now I can take an exponent both the sides, right? If I take e raised to the power p 2 pi d n cap dot r 2 pi into m dot p. What is this thing? 1, right? This goes to 1. P into 2 pi d n cap dot r. This is the modified equation for family of planes. This time I kind of did it much more neat. Last time the derivation was little messy. Yeah.
Sir, यहाँ पर iota है.
Oh yeah, thanks for correction. Yeah, thanks. Yeah, iota should be there, and that's why if iota is near, it can't be. So thanks for correction. Okay, so this is iota p, where I know the p belongs to a integer. Okay, good. So this is the equation for the family of planes, and I'm happy. So now the claim is this p is always an integer, right? Okay. So the smallest value it can take is 1 as an integer, right? It can take 0, but 0 is, if I take exponential of 0, that is 1, 1 is equal to 1. Just there is nothing interesting in it, right? Okay. Now comes to the claim. Claim is in this lattice planes, right, that I drew earlier. So these were my lattice planes for which I wrote this equation. There exists a vector, reciprocal lattice vector k, which is perpendicular to it. So what I am saying is, there exists a reciprocal vector k which is perpendicular to all this thing. And the minimum magnitude of this k, 2 pi by d. Okay. How do I know something is a reciprocal lattice vector? If I have to say that there exist and all those things, this is like a complicated mathematics jargon. But how do I know which equation which tells me k is a reciprocal lattice vector? So let us see what was the condition that the formal definition gave. If k is a reciprocal lattice vector, then this condition has to be true, right? So the condition was, okay. So e raised to I k dot r is 1, right? Okay. So we will come to this equation. So the condition was capital K dot R has to be 1. Right? This was the condition. So we are not establishing this proof at the level of mathematical rigor. What we are not doing is we are not establishing necessary and sufficient kind of thing. I am establishing one-way relation and assuming the both-way relation hold, which is like a little less rigor than the mathematician, because mathematician will establish a condition for sufficiency and necessity, right? We will not do that because that would be too much for this course. So, okay. So this is condition for lattice. So if this condition is true for a reciprocal lattice vector, right, with k has a minimum magnitude of 2 pi by d, right, then I can always say this is, and the equation of plane is this, right? Then I can always say this is the condition for, so not condition, this is the equation of a plane. For any lattice point, here R was a continuum vector, right? For any lattice point, this R has to be capital R, right? This is the Breve lattice vector. If I want to go to any lattice point, I have to, instead of R, I have to put the capital R, right? So if I put here R is to capital R, I got this equation, I capital R dot, capital K into capital R is 1. That implies this K has to be, belongs to the reciprocal lattice vector. Right? And why I am saying it has the minimum magnitude 2 pi by d, if it doesn't have if it has a lesser magnitude than this, what will happen? This equation of plane won't be satisfied, because here the p can be, the least magnitude of the p can be 1, right? So okay, so what we have got basically, I have a lattice set of planes, and I know that if I take any 3 lattice point, make a lattice planes, right, and then the spacing between them is d, I know there will exist a reciprocal lattice vector that is perpendicular to them, which has, and there is a lattice vector with the smallest one, right, with the smallest magnitude 2 pi by d, right? But we have got, for any family of lattice planes, there exists a reciprocal lattice vector perpendicular to family of plane with minimum magnitude being 2 pi by d. So you cannot have a reciprocal lattice vector that is perpendicular to this family of plane with magnitude lower than this. So okay, good. So we are kind of done. So now I will have one more statement, that if you cut a lattice, take a 3 points, make a plane, and then you make a family of plane by some distance d, next 3 points and all those things, right? So these lattice plane will cover all the lattice point. That's another claim. One family of plane is sufficient to capture all the lattice point. Family of lattice plane is good enough to capture all the lattice points. How do I prove it? How do I prove this statement? Okay, I will say this is the equation of a plane. Now I can just, instead of R, I can just put a reciprocal lattice vector K, right? This is the equation for family, right? How do I say every point will be covered by this family? How do I say that? Every point can be described by a capital R vector, right? Okay. Here K, capital K belongs to reciprocal lattice vector. Every point in lattice is by a R vector. So if I replace R with the capital R, what should happen? This equation should be true. Capital K dot capital R is 1. Is this equation true always? So this was the condition for the reciprocal lattice space, right? So this condition is always true. So what does it mean? It means the statement that I stated, this statement, lattice family is good enough to capture all the lattice point is true. Okay, so now what we can do, we can identify a lattice family. I take a lattice family, right? Lattice plane family by some numbers. It's and the identification of a lattice family by some number is called the Miller indices, right? What we can do, I have these lattice planes, and I want to tell you which lattice plane I'm talking about, right? One way I can tell you, tell me what is the reciprocal lattice vector. Because if I give you the reciprocal lattice vector, the smallest one, you know the two things. You know what planes are perpendicular to it, and you will know what is the spacing between the planes, right? To know the family, you just need two things. What is the spacing between the planes and what is the perpendicular vector, right? So what you can do, if I give you the K with minimum magnitude, that is perpendicular to lattice plane family, you will know what family I am talking about, right? So the Miller came up with a procedure to kind of tell you what is how to identify a family very quickly, and you will see it's very simple procedure but very powerful procedure, right? Okay, so I know that the K has this thing, the minimum one with the minimum magnitude is 2 pi by d into n cap, right? N cap is the perpendicular to this lattice family, right? Okay, and I know that how I write any reciprocal lattice vector. How I used to write any reciprocal lattice vector. If I want to write a general form of reciprocal lattice vector, it was H into B1, K into B2, L into B3, right? H into B1, K into B2, L into B3, where B1, B2, B3 were reciprocal lattice primitive vectors, right? Reciprocal lattice primitive vectors, they were B1, B2, B3, and H, K and L are integers, right? They have to be integer. Okay, good. So what I want, let us say if I have, okay, okay, so let us say I have this, A1, A2 and A3 axis, right? In the direct lattice, I have this axis, right? A1, A2. So A1, A2 and A3 were the direct primitive lattice vectors, right? A1, A2 and A3. Any family plane, right, that I'm talking about, any plane that I'm kind of talking, right, family of plane, it will cut somewhere these direct lattice axis, right. Let me call this, either it will cut or it will not cut. If it doesn't cut, I will say it will cut at infinity, right. So let me say there is a cut called at x1, there is a cut called x2, and then there is a cut at x3, right. Okay. So what I can say in this, what is the equation of this plane? That was capital K dot R is 1, right? Or I can say the equation of plane is capital K dot R is equal to 1, or sorry, 2 pi into n, right? I can always say that. And let us say if it cuts at x1 location, right, what I can do, this equation shall be true. What is this coordinate of this point? Here R would be, at this point, what is R vector? I can say this is x2 into A2, right? What is the position for this one? This is x1 into A1 vector. What about this point? x3 into A3 vector, right? x1, x2 and x3 are the intercept, right? So what I can do, this equation, I can write it in 3 different equation, right? This has to be true all the time, right? I can put this K here and these are here, and then I can get 3 equations, right? Okay, let's do that. If I have it, then why don't we do it? And I know that AI into Bj is 2 pi into delta Ij, right? Okay, so let's do this. This is H into x1 is equal to 2 pi into n. K into x2 is, okay, so the 2 pi will go anyway because there is a 2 pi coming from here, and it could be any integer, so let me put n1 . Okay, so this is n, this is also n, and this is k into x3 is also some integer. Now what I can do, I can take the ratios, right? What I can do, I can take the ratio h ratio k ratio l is equal to 1 by x1 ratio 1 by x2 ratio 1 by x3 ratio. What I can do, I can just take the ratios, right? If I have these 3 equations, I just take the ratio, and the x1 will go, because these are just some integers, right? These integers will cancel and I will get h ratio k ratio l is 1 by x ratio 1 by x2 ratio 1 by x3 ratio, right? Okay, now the condition is, so if you see this vector, right, this reciprocal lattice vector, to know its HKL, what you need to know the plane. Take one plane and see where it is intersecting the axis, right? And take those HKL which doesn't have any common minimum factor. If it has any common minimum factor, what will happen? It will not be this minimum k, right? It will be 2 pi d into some n time, right? If it has a minimum common factor, then that is not the k with the minimum magnitude. I want the k with the minimum magnitude. It would be the one where h, k and l doesn't have any common minimum factor. So the h K and L doesn't have it should not have a common minimum factor, then I can say I can get the HKL basically. Take the ratio, multiply anything and just get rid of all the common minimum factors and any fractions, and HKL has to be integers, right? If these two conditions are satisfied, from the directly by looking the plane where they intercepted, I know what is the K vector that was perpendicular. It's a very powerful statement. I took a crystal lattice where it intercepted the axis, I got what is the reciprocal vector that was perpendicular to it, right? And this reciprocal vector is called the Miller indices. This HKL is also called the this is not the, this is the regular Miller, not the beer, right? There is a beer called Miller, right? Okay. So this is the Miller guy. So this is the Miller indices. Okay. I thought everybody is kind of getting dozed off. So I should say something which wakes you up. Okay. So are we good? How do we get the Miller indices? Once we know the Miller indices, we know what is the direction perpendicular, we know what is the reciprocal vector, right? Okay, so we can have a nice procedure. This is like all proof, and we can have a nice procedure to to get the Miller indices of a plane. Take a plane, set up the axis, right, along the edge of a unit cell, or set up the axis along the primitive lattice vectors, right? Or the lattice vector in general. Here, if you see in the procedure, I have just said a unit cell. This is true for cube only. But let's say you are a hexagonal system. Then you have to set up an axis along the this primitive lattice vector. You take a primitive lattice vector, set up an axis, and then you find the intercept where the things got intercepted, right? And let us say the intercept was 2, 3, 1. Take the inverse of it, 1 by 2, 1 by 3, 1 by 1. And now the HKL has to be integer, multiplied with something that makes it an integer. What should I multiply if I want everything to be integer? 6, right? So if I multiply with 6, I get integer. You see here, it doesn't have any common minimum factor. This 3 to 6, you can't bring any integer out of it now. So then this is a valid Miller indices, right? Okay. So this complicated proof, I'm not sure whether you will find it in books, but at least in the semiconductor one. Okay. But this is how they identify a plane. So to reach the Miller indices, I took a very inverted route. Went into reciprocal lattice, came from there, but there is a point that I want to convey. If you have planes, there is a reciprocal lattice vector perpendicular. That is very important to know. Why I want to convey this point? Because when we make this wafers and you want to, and we will see, in later classes, the direction in which the reciprocal vector is there, your momentum of the electron also have many times take that direction. So you need to know where the electron is moving, kind of. So all this thing. Okay, so this is an example. Let us say what happens if the intercept is at the negative axis. Let us say I have this axis at x, y, z, right hand coordinate system. I will take an inverse of it, multiply it with 6, I will get this, right? Now if you have one index as a negative, you just put it as a bar. What happens if your plane passes through origin. These Miller indices are not for a plane, it is for the whole family, right? If your plane is passing through an origin, what you will do? You will take the next plane which is not passing through the origin, right? The Miller indices are not for a plane, it is for the family of planes. If one plane passes through origin, just take what is the, in that family what was the next plane. That's it. Right? And if a plane doesn't intercept, that means it intercepts at infinity, right? It's like a mathematical abstraction. Where do the parallel lines meet? At infinity. Okay. So let us say this is, it is intercepting here 2 and it is intercepting here 3, and on the z direction it is not intercepting at all. Then these are the intercept. You take an inverse of intercept and multiply it with 6, you will get 3, 2, 0. One thing, if you see in the Miller index any 0, that means you should ring a bell that the plane, there is at least one axis where plane is not intercepting at all, right? Okay. So now comes, how do I, so there is a convention. When I write a Miller indices, I put this curvy linear bracket. I just put this normal bracket. That means these are Miller indices, right? Okay. Now coming to this equivalent plane. We saw that a cube, right? Cube has a threefold 6 axis of symmetry, right? You can kind of take a cube, pass a body diagonal around it, fold it around by 120 degree, you get the same cube, right? So because of these symmetries, many Miller planes are same. They may be different in their numbers, but physically the atoms are going to look exactly same. So these are called equivalent planes, right? So in the cubic system, since the cubic system has this threefold, axis of body-centered axis of rotation symmetry, so these are the equivalent plane. So the question is, how do you know which is the equivalent plane? You can just check it on internet, or when you are doing some inventing, making some new crystals, the crystallographer, take a great amount of care which are the equivalent planes and all those things. So, but for cubic system, that is there for this semiconductor devices. Most of the semiconductor devices are cubic. So we are kind of, we just know these are the sets and we go with, let us say this 1, 1, 1, 1, 0, 0 has this 1, 2, 3, 4, 5, 6, 6 equivalent planes. So you put a curly bracket to show that 1, 0, 0, it has many equivalent planes and these are the 6 equivalent planes. So that's it. Similar to the Miller indices, we have Miller directions, right? We got the Miller indices for a plane, right? Now we can say, okay, if I have any vector n, any direction that can be decomposed in the a1, a2 and a3, they are direct lattice primitive vectors and HKL, right? I can decompose any direction in the real space in terms of the primitive lattice vectors. So you call these, HKL. If you take any vector, decompose it in the, in the primitive lattice vectors, and whatever HKL you get from that decomposition, you call it a Miller direction, right? And for the direction, you put this, square bracket. Let's say 1, 0, 0. This is a square bracket. Okay. So this is CAQ, that stands for class assessment question. You can try it at home. In a cubic system, a plane and a direction with the same indices are orthogonal to each other. If you take a cubic system, right, and you take a Miller direction, and let us say you are talking about this is the direction I am talking, and this is the Miller plane I am talking. So they will be perpendicular to each other. How do I know it? Because if this 1, 0, 0 is the direction, right, and 100 is the plane. The 100 plane has to be kind of perpendicular to 100, right? So you see this, I mean, this is a very simple proof. You can go and try it at home. Okay. So these are the conventions. Similar to the equivalent planes, we have equivalent directions because of the symmetry. So you have this curvilinear bracket for the crystal plane, square bracket for the crystal directions, and curly bracket for equivalent plane, and this wedge shaped bracket for equivalent direction. This is just convention. How do I get an angle between these two planes? If I have two planes, how do I get an angle? I can just take the dot product and find the cos, right? It's like as trivial as it. Okay, now one of the application that this Miller indices are used when you take a wafer. I guess you will be taking Professor Satinder course, right? The semiconductor fabrication in the next semester. There you will going to see wafers, right? And have you seen the wafers in the lab? Okay. So when you take a wafer, it is grown along a particular direction. Let us say it is grown along 100 direction, because the fabrication process is such that when you take a wafer, you are going to grow it in a specific direction, right? And there, I want to say, okay, give me a wafer grown in 100 direction, or give me a wafer grown in 111 direction, right? Then what I will do is I will go through crystallographer, I will ask them, they will give me the growth rate. Right? So once the somebody has given you a grown wafer, right? There are two ways. He can say, he will just put it in some nice packing and say, this is the wafer grown in this direction, and this type of doping is done, and you use it, right? But generally, what these growth people do, they put some certain type of cut in the wafer. And I'm not sure whether they are doing right now. In earlier time, they used to be cut, but now I heard some of the growth wafer, they are not putting even cut, they are just putting a small notches, right? So they put some kind of a cut, and there is something called primary cut. Primary is the one with a bigger cut. You see this is a primary flat cut, you put a bigger cut, and then you put a secondary cut. The primary cut tells you what is the orientation of the wafer. Let's say whether it's a 111, 100 or something like that, right? And the secondary cut used to tell you about the doping. Now they put a notches, and the doping information, they will say, check the data sheet. You will put it in along with the wafer, they will give you data sheet also. And why this direction is important? Because you know that these are crystalline systems. Semiconductor is a crystalline, right? And you might have heard the crystalline system, their properties varies from direction to direction, right? If you take a crystalline system, if you measure the, let's say, electrical conductivity in this direction, this will be different, this direction it may be different, right? So when you make a device, it has to be aligned in a specific direction. So these cuts are put when you are going to make a device, you can identify which direction you need to align your wafers and the devices, right? So let us say this is one very I guess for the device application, now they use 100, right? Earlier for the device application, back in old time, they used to use 111. Now they use 100, and this is like a 100 wafer which has a primary cut, and the cut direction is 011. So you see this, you take a wafer, let's say if I have a chalk, you take this wafer and you put a cut like this, and I'm saying this is 100 wafer. The plane is 100. So there is a family of planes, and wafer is grown along that family of plane, and this direction is 011. You see this This I'm putting a curvilinear bracket that I'm telling this is the like a plane direction, and this one is the like a Miller direction. This is the Miller indices for the plane. This is for the direction. So you cut this and this perpendicular line. I'm kind of calling this. And now if you take the dot product of this and this, it will come 0. That means this line is perpendicular to this, right? So this is, and so you know where is your this 0 1 1 direction is, and where is your 1 0 0 plane is, right? Now you can identify, if I in a plane, if I know the two directions, I can identify any direction, right? If I have plane, I can identify what is this direction and okay. So you know, a small example is given. Let's say here, let's say you have 0 1 1 direction and 1 0 0 direction is known, and let us say you want to find 0 2 1 direction, and you want to align, I want to align my devices along 0 2 1 direction, right? For my you see here, first of all it has to be in the plane, and what I can do, I can find this cos theta 1 by taking a dot product, and here it is 1, you see 1 0 0 0 2 1, and you're normalizing it with the magnitude 1 by root 5, and this is the theta. So first thing I establish this 0 2 1 lies in the plane. It has to be in this plane, right? If it is somewhere here, I mean, I cannot make a device in the air, right? Okay. And another angle, I can find out what is the angle of this direction. Let us say I'm talking about direction called 0 2 1. So in the slide, I have used a different color, so you will know which color it is. I'm just doing it for the sake of simplicity here. So what I can do now to find this theta, I can take a dot product and say, okay, so the cos theta 1 here, let's say, sorry, cos theta 2, you see this cos theta 2 here, this is dot product between these two vectors and normalized to their magnitude, and this theta 2 will come out to be 18.5 degree with respect to 0 1 1 direction. So this was 0 1 1 direction, and this is 0 2 1, and now I can make a, let's say, some device, some pattern I can make this way, right? So this is how the Miller directions and planes are used, and you can get in the assignment there will be some questions and you can solve it and get a better feel, right? Okay, so this is like a very quick rundown, hard sphere approximation, and this is the I guess you might have, all of you might have done it at your +1 2 level, right? So if I have a cube and if I assume instead of atoms I have spheres, and I keep increasing the spheres such that they start to touch, right? What is the maximum I can fill the cube? Okay? This is the hard sphere approximation, because when you are going to get the any crystal, right, you will have some packing densities. So this hard sphere approximation will give you, this is the like upper bound. You can't get more than this, right? Because the atom is not a hard sphere. Hard sphere is like a kind of cartoonish version, but this gives you like an upper bound. So if I have a simple cubic, and it's very simple to do this calculation, and it has atomic fraction of 0.52, and if you have a body centered, it has a higher packing density around 68%, and FCC has the highest around 74%, right? So I'm not going through it, it's given in the slides, you can read it, it's very, and I'm sure all of you might have done it at your +1 2 level, so I'm just skipping it. Okay, so now coming to the crystals of common semiconductor. So the common semiconductor that will be addressed in this course are silicon, gallium arsenide and germanium, because most of our devices are out of these crystal systems. And so let us see, okay, let us see what are the crystal lattices system that we have for various semiconductor called silicon, germanium and let's say carbon also. So silicon and germanium, they have the diamond structure, Okay, so the structure is you have two FCC lattice and they are diagonaled by 1/4 along the body diagonal. You take a cube, you say you have a cube and then you move it by a 1/4 distance along the body diagonal, and this is how you get the two FCC offset by the in each direction, or FCC. So this is the one way. This is the one of the possible way to understand. The first one is one of the possible way, and the other is you take a FCC structure and on each point in the FCC lattice you put two atoms. So you will have this like these two atoms on each FCC lattice. If you put it this way, you are going to reconstruct it. So this is the like basis. So there are two equivalent way of imagining the how do you construct a silicon or germanium, right? So the number of atoms you will get in a unit cell is 8, and the coordination number means how many the closest neighbor it has is 4. And if you calculate the packing fraction for the silicon, it will come out to be around 34%, right? So this is a very simple calculation. This is the like and this is like a hard sphere under hard sphere approximation. You assume each silicon atom is like a sphere, and you keep increasing its size till it touches the other sphere, right? So this is the maximum fractions packing fraction you can get. You can't get if you have why we needed this maximum fraction. Let us say you are some crystallographer, right? And you did some XRD and all those analysis, and you predicted this is the crystal. I am having a cubic crystal, and I'm getting a packing fraction of, let's say, 60% with simple cube. I say this goes beyond the hard sphere approximation, so that means you might have done mistake at some point. It's like that kind of a. So this kind of tricks are very essential when you solve a question using ChatGPT. You should know how it has screwed up. Okay. And the other thing is we have this gallium arsenide. Gallium arsenide is heavily used in the optoelectronics. So we will have some few words during the course for the gallium arsenide. Not few words. We will treat it on a more or less equal footing that of silicon and germanium. And conceptually gallium arsenide will come out to be more easier. We will see that. And it has similar thing, but it has zinc blend. In the silicon, it has all the atoms were silicon of same type. In the gallium arsenide, you have basically gallium and arsenic, right? So it's a 2 FCC, but one of the FCC is made up of gallium and other one is kind of made up of arsenic. Or you assume each has this basis structures with one gallium atom and one arsenic atom. So it looks like a diamond, but the atoms are different. So that's why its structure is called zinc blend. Why it's called zinc blend? Because zinc blend structure was discovered earlier. So when they found gallium arsenide, they said, okay, it looks like a zinc blend. Okay, good. So yeah, so that's it. And so each gallium atom is surrounded by 4 arsenic atom, and each arsenic atom is surrounded by 4 gallium atom. And similarly, each silicon atom is surrounded by the 4 silicon atom. And it has a sp3 hybridization, right? In the language of a chemist, right? Okay, so with this we complete our study of the crystals, right? And then we shall meet next class for start of a new chapter about the quantum mechanics. And in the next week we will have a quiz about the crystals.